Okay, so welcome to this new episode of the EROSS series of seminars. These are the ER online summer seminars. And today we have Maurizio Lenzerini, he's a professor from the University of Rome La Sapienza in Italy, my alma mater. And his talk will be on query answering and query abstraction through ontologies. So Maurizio in Rome leads a group which is probably the research group, which is probably the most important artificial intelligence group in Italy since many decades. And this group works on knowledge representation, reasoning, database theories, ontologies, information systems in general, robotics, and all sort of AI stuff, I guess, more classical in the more classical sense. When I was a student, he was already a professor, a very young professor. And in Italy is the top computer scientist, so he has the highest age index among all Italian computer scientists, and apparently, according to some rankings, he's the 85th in the whole world best computer scientist. And as I was telling, his main research is on automated reasoning with ontologies and conceptual schemas. And he did study a lot the connection with databases. And he has been a pioneer in his group and himself personally, a pioneer in formalizing description logic, so the language, the formalist which is behind the more recently web ontology language OWL, and applied this to reason with conceptual schemas in the broader sense. In fact, this is a very old, well, the correct word is old, but this doesn't mean that he's old, but a very paper for a few decades ago was the first formalization in logic of the entity relationship diagrams. So it's strongly connected with ER. And he developed these ideas to create this new paradigm, which is called ontology-based data access. So how to connect ontologies with databases technology. And in parallel, he did work on conceptual-based information integration and data exchange, data warehousing. He introduced a number of formalization in semi-structured data, view-based query processing. He worked on e-services, more in general on database theory and logic and computer science. In spite of being a top researcher, is also a very good educator. Again, I remember when I was a student, I've learned a lot in discussion with him and his group. He wrote several textbooks on databases and also on software design. And of course, he has a number of research recognitions. He's an ACM Fellow and AAAI Fellow. AAAI is the association, the international association that gathers all artificial intelligence researchers, and was mainly based on the States, even now. Now has become worldwide. It was also fellow of what is now called EurAI, which is the European Association of Artificial Intelligence, but he was a fellow already when he was still called IJCAI. He's member of Academia Europaea, and I will have to ask him after his talk what this means, because I have no clue what Academia Europaea is. And of course, he's an ER Fellow, so he's completely in line with this series of seminars. So I think we are going to enjoy a lot this talk by Maurizio. So Maurizio, welcome to EROSS.
Oh, thank you, Enrico, for this very, very nice introduction. So when I had the invitation of this to this seminar series, I was very interested because what it attracts me was the acronym. I mean, EROSS. So that's it's becoming a very interesting event. Then I wanted to have a look at some of the presentations of previous speakers. For example, Nicola Guarino was, I think it was the first talk here in this seminar series. And the first slide of Nicola was going like this: joint. So we have EROSS joint. That's very, very interesting. I mean, it was becoming very interesting. And finally, I had a look at the presentation by Van der Waast, and I found rock and roll. So I have, the three pillars of my generation: sex, drugs and rock and roll present in this seminar series, which is becoming one of my favorite seminar series. Okay, so thank you for the invitation again. So what are we am I talking about today? I'm starting with an observation about the role of conceptual modeling in the 70s. When I started my master thesis, it was the time where my professor Carlo Battini was somehow introducing the notion of conceptual modeling in Italy. And I learned what conceptual modeling was. I mean, at that time, you should know that at that time, database design was essentially, the activity of drawing some tables, maybe with the help of functional dependencies and normalization. But designing a database was just the process of defining and deciding which tables you should have in your relational database. After the work by Peter Chen and others, some people, put forward the idea of designing a database in a completely different way. So first of all, design a conceptual schema, which was, an abstract representation of the data that you want to store in the database independently on the technology, and then from the conceptual schema, produce the database, the logical and physical schema of the database during an implementation phase. So you see here, the idea of the conceptual schema at that time was a design time idea. Why? Because at runtime, the conceptual schema disappears. And then the user directly uses the database with no concern about the conceptual schema. So I was just puzzled about this idea of using something useful during design time, but then not having it at runtime. And I think that looking retrospectively to my research career, I think that one basic research question that was very, very important for me was why not using the conceptual schema at the runtime? Okay, so I was looking for principles and tools. After my master's thesis, I was just looking for principles and tools for using the conceptual schema at runtime. With the conceptual schema at runtime, the user, instead of using directly the database, it should use the notional conceptual schema, which hopefully is more fun, is more useful for him because it is a conceptual representation. It should be closer to the idea of the user, closer to the mentality of the user, to the concept of the user, closer with respect to the database, which is a technical thing, which is a technical artifact. So that's the idea. Why not using the conceptual schema at runtime? To make the story short, something like 15 years ago, my colleagues in my group and me, we came up with the idea of ontology-based data management system. What is it? It's a very simple idea. You express the conceptual schema, let's call it ontology, as a declarative logic-based specification of the domain of interest, and then you connect the real database, which is the real data sources that exist, and they are used by applications. You connect it through the notion of mapping. So in this way, the software, the programs of some of the users should still use or could still use the data sources as they are in practice designed, but some other users can exploit services at the level of the ontology. So this kind of user here that would like to have a unified and conceptual view of the data sources could use this artifact, which is the ontology. And the basic difference between the ontology and the data source is that the ontology describes the domain of interest. They are not describing the data per se. The ontology describes the domain of interest in terms of concepts and relation, and probably in terms of an abstract representation of these things. And the mapping is, the technical tool that is able to connect the data at the data sources to the concepts of the ontologies. Okay, and actually, this kind of abstraction was, very useful because if you think about it, this very simple idea of separating the domain of interest, with respect to the technical artifact of the data as managed by systems, in applications, this idea can be applied in several contexts where data interoperability is an important factor. For example, we can realize the notion of data independency with this abstraction of ontology-based data management. Why? Because data independence means that the user can see an abstract representation and is not really a slave of the application-oriented aspects of the data. Data integration can also be seen in this light, because the unified schema, let's say, a unified view that you offer to the user can be represented by the ontology, and the real data sources that are, probably heterogeneous and independently developed are connected to the ontology by means of the mapping. Data exchange can also be seen, in this light, and also many other data interoperability architectures. Okay, so if you buy the idea that ontology-based data management is a good idea, a good paradigm, then probably the talk that I'm going to provide you is an interesting one. Why? Because we are focusing on this paradigm, and my goal is to deal with two specific problems that now I want to introduce. But first of all, let me tell you that probably, besides the ontology, the most important part of the system of an ontology-based data management is the mapping. The mapping is a set of assertions, or at least I consider the mapping as a set of assertions. Each assertion tells something about the relationship between the data sources and the ontology. And I would like to, to fix some basic notion that I'm going to use in this talk. Each mapping assertion is essentially an implication, right? As far as this talk is concerned, each mapping assertion is an implication of the type: for all x, phi x implies psi x, where phi x is a query over the data sources whose free variables are x, and psi x is a query over the ontology, right? In this case, node S and node G represents the sources and the ontology, whose free variables again are from X. So it's an implication from one query at the level of the sources to a query at the level of the ontology. And we say that the intuitive semantics of each assertion is that whenever the data items in the schema, in the source schema, on the source database, satisfying the pattern expressed by the query, okay, then these data items, somehow makes some other patterns in the ontology true. Okay, so please consider that there is a flow from the data sources to the ontology. So if something happened in the data sources, then I know that something is true in the world of the ontology. So that's the kind of mapping that we are considering. And actually, if you look at the literature on data integration and data exchange, there are three kinds of mappings that are very, very popular. You know, one kind of mapping, it's called GAV, Globalist View. You have the restriction of using only one element in the ontology. So it's a kind of restricted mapping where you just map a pattern in the data to a single element in the ontology. In the other, let's say, paradigm, in the other restriction of this kind of mapping called LAV, localized view, you have somehow the opposite situation. You map one data source, right? One atom, one data source to a pattern in the ontology. And the most general kind of mapping, we call it GLAV because it's a combination. In this case, just one query is mapped to another query at the ontology level. Okay, I introduced this idea, this terminology, because it will be useful during the talk. Okay, just to give you an idea of a mapping, this is a mapping where you have a query on the left, which is a query at the level of the data sources, which is mapped to a query on the right, which is the level of the ontology. This kind of mapping says that, for example, if you have a student X in the sources with a grade for a course Y and a value of the grade Z, then these patterns corresponds to another pattern in the ontology, because if this happens, that you know that there exists a teacher teaching the course Y, and you know that student X is enrolled in the course Y. So you see how the mapping works. If something is true in the data sources, some other things are true at the level of the ontology. Okay. Now, the idea of this talk is which are the mechanisms, the basic mechanisms by which I use the mappings when I want to process queries in ontology-based data management. Okay, so I mean, if you think about an ontology-based data management, you have a lot of problems, technical, methodological, you know, but here I focus on one particular problem, how to process queries in a system that has, you know, follows the paradigm of ontology-based data management. So the talk will be, you know, this will be structured as follows. First of all, I have to tell you something about ontology-based data management paradigm, a little bit more technical. Then I will introduce the two way of processing queries in ontology-based data management that I call answering and abstraction. Then I will go into the details of both problems, both aspects, and then I will draw conclusions. Okay, so what is more technically an ontology-based data management? So, I mean, from an abstract point of view, you can consider an ontology-based data management as a triple: an ontology, the mapping, and the schema of the data sources. Okay, so now I'm talking about an ontology-based data management specification, right? A specification is, you know, it's a kind of schema of the whole thing. Then I will obviously pair the specification with the data. But for the moment, O is an ontology, M is the mapping, and S is the schema of the data sources. Now, O is the ontology expressed as a logical theory. Okay, for me, an ontology is always expressed in logic. I know that you know, probably many people say that's not the only way. But I'm okay with that. But here we assume that an ontology is a logical theory, so it's a set of logical axioms. And in particular, I'm assuming that I'm going to use a description logic to express the ontology. So in the terminology of description logic, an ontology is a T-box. It's a set of axioms giving, you know, the real intended meaning of concepts and relations that are in the ontology. S is a data schema. Essentially, it's a schema of the data sources. For example, it might be a relational schema, or it might be a federated relational schema, combining schemas of different kinds. Okay, but it doesn't really matter. It's a data schema. I'm assuming in the talk that it is a relational one, but it might be a different kind of schema. And a mapping assertion, M is a set of mapping assertions having the form that I talked to you about before. But look, with the restriction, from now on, the query at the sources and the query over the ontology, they are conjunctive queries. Okay? A conjunctive query is a very nice kind of query in logic, which is conjunction of atoms, and it corresponds to select project join in SQL. So it's a very popular class of queries. So let's assume that in this talk, that essentially the the queries that appear in the mapping assertions are conjunctive queries. Okay, now suppose you have an ontology-based data management specification, or BDM specification. Obviously, you get a real thing when you have the real data at the sources. So an OBDM system is a pair, which is constituted by a specification, an ontology-based data management specification, plus a database for the schema S. Okay, so when you have the pair J, which is an OBDM specification, plus D, which is an S database, a source database coherent, legal for the schema S, you now have an ontology-based data management system. Okay, so that's in this slide we have an example of specification. Okay, here you see there are no data here, but we have an ontology, we have a schema, a source schema, and we have the mappings. Let's spend 2 minutes to look at this specification. You see, the T-box, the axioms in description logics that you find in the ontology O is a set of axioms that essentially formalize an UML diagram. Right? For example, I have a concept employee. I have 2 attributes, emp code and salary. I have another class which is project, which corresponds to a concept, a predicate, a unary predicate project, with attribute project name, which corresponds to a binary relation. And then I have a binary relation works for in such a way that work for every pair X, Y satisfying the relation, the predicate works for, I know that X is an employee and Y is a project. So these kind of diagrams can be captured by this kind of ontology T-box expressed in a description logic. Okay, I'm not going into the details, but it is somehow obvious that you can draw these axioms in description logics in order to describe your domain. You see the point here. There are no data yet. There are no real database implemented yet. It's just the domain that you describe independently from every technical artifact. Now let's go to the federated source schema. Let's say that you have a schema in a relational model, and therefore this might be provided by an SQL endpoint. You have 3 relations. For example, you have D1, which is the relation. It's a table where employees and projects they work for are stored. You have another table like code salary, and therefore this table tells you the salary of employees denoted by codes. And then you have a table that puts in correspondence the code of an employee with an SSN of an employee. So it's a kind of table that allows you to know which is the SSN code, SSN number of an employee given its code and vice versa. Okay, so that's the real data. Okay, this is the real data you might have in your database. This is your domain, and now if you want to complete the OBDM specification, you have to write the mappings. And for example, let's consider the second mapping assertion. The second mapping assertion says that if you do the join between D2 and T3, right, on the basis of the equality on codes, then you obtain some data that would correspond to the following facts in the ontology, at the ontology level. First of all, you would know that every person built on the social security number is an employee, because you know the semantics of the tables, and therefore you know that this pattern corresponds to the idea that, or to the fact that a person corresponding to the social security number that you've retrieved from the table is an employee. And then the salary of this guy is exactly the value that you find in the table D2. Okay, so that's very simple kind of mapping. Similarly, you have the other kind of mapping. Okay, so that's the ontology data management specification. Now, let me just discuss about the semantics. I think it's very important that we fix the semantics of the whole thing. Otherwise, all query answering obviously is based on formal semantics, right? So let's spend 2 minutes to talk about the semantics. It's actually very simple, but let's do it. First of all, since O is a logical theory, you have to consider as possible semantics the interpretations for the logical theory O. So let I be an interpretation for the ontology O. A first order interpretation, which is constituted by the domain of the interpretation and the interpretation function. This is the first order logic interpretation. What is the semantics of J? Well, the semantics of J is given always in terms of an S database D. So you don't have a semantics of the system if you don't have a real data at the sources. So you start with an S database D. Remember that an S database means that D is a database coherent with the structure of the schema X. Now, you take an interpretation I for O, and you say that this interpretation is a model of the whole system, the system constituted by the pair JD, if I satisfies all the axiom of O, which means is a model of the ontology. I mean, if I is not a model of the ontology, it cannot be the model of the system, because the ontology fixes, the semantics of our domain of discourse. And the second point is that I satisfies M with respect to D, which means that every assertion in M in the mapping is satisfied. So the implication corresponding to the assertion of M for each assertion is true in the model corresponding to I and the data D. So in 2 words, the semantics of the whole system is such that the interpretation that forms the semantics, the models, should be model of O and should satisfy the mapping with respect to the database D. Obviously, we also say that JD is satisfiable or consistent if it admits at least one model. Look, it might be that JD is not consistent, so no model exists. It may be that no model exists for the pair JD. But if at least one model exists, then we say that JD is consistent or is satisfiable. And finally, suppose we have a query QX posed to the ontology-based data management system JD. So what is the semantics of the query? Right? What is the semantics? I mean, we are not in the realm of database. We do not have just a database, right? Because remember, Q is a query over the ontologies, not a query over the data source D. Q is a query over the ontology. So which is the semantics of this query? Well, one very popular way to give a semantics to Q is to to define the notion of certain answers. What is the notion? What is a certain answer? Well, it's an answer of Q that holds in all possible models of JD. Okay. So I'm going to consider as the semantics of the query all tuples that satisfy the query in every model of the system JD. And every tuple that satisfies the query in all the models is called a certain answer. Why certain? Because if it is, if this guy satisfies the query in all possible models, there is no uncertainty. This is really an answer to the query. Okay. Well, let me just skip this slide, okay? Because I want to go now to the real, to the core of my talk. Now we know what the semantics of an ontology-based data management is. We know that semantics of a query posed to the ontology is. And now I want to talk to you about two fundamental problems regarding queries, right? Well, the first one is obvious. How should I compute the certain answer? How can I compute the certain answer? Which algorithm should I use to compute the certain answer when I have a query QO over the ontology O in the database, in the ontology-based data management specification J? Well, one way to do it is to rewrite the query. Okay, so the question under the query answering problem can be put as follows. Given a query Q over the ontology, compute a query QS over the data schema that captures the certain answer to QO at best under J. So remember, the real data are present in the sources. So it's very natural to ask ourselves, given a query QO, how should I extract the certain answer from the data at the sources? This means, which query should I evaluate, should I execute over the data sources in order to exactly get the certain answers of the query at the ontology level? Okay, this is the query answering problem, and more specifically is the search for a direct rewriting. So I want to rewrite the query QO using J in order to get a query at the sources that, when executed over the sources, it gives me the certain answer to QO. This is called direct rewriting because I go from the ontology level to the source level, from the query over the ontology to a query over the sources. And as I will tell you in a second, this is a very studied problem, an extremely investigated problem in the last 15 years. How should I answer a query over the ontology by accessing the data over the data source? But there is another nice problem, which is somehow the opposite. Given a query QS over the source schema, which is the query over the ontology that captures QS at best under the OBDM specification? So in some sense, if the ontology to source rewriting is called direct rewriting, here I'm talking about a reverse rewriting or a source to ontology rewriting. So instead of doing top down, now in this case I'm going bottom up. And these two problems are extremely important and, crucial problems in ontology-based data management. For example, query answering is obviously the task that you want to use to compute a certain answers, but you could do query answering for doing other things. For example, to check the quality of the data, right? Because what you can do with query answering is to compare the ontology, the word represented by the ontology, with the data that you find at the sources. And therefore you can come up with queries at the ontology level that looks for violations or conditions for high quality data. Therefore, I don't have the time to prove this, but I can assure you that query answering is a basic task to check data quality through ontologies. Query abstraction, which is the other task here, going from the sources to the ontology, can be used in many different and interesting ways. For example, if I ask an ontology-based data management system, give me the content of the data source, what do I find in this data source? Well, if you do query abstraction, you may come up with an expression at the level of the ontology that explains the content of the data source in terms of the ontology. More interesting, if you have a data service expressed at the level of the data sources. Now, many people in software engineering talks about microservices, right? Microservices use their own data sources, their own data structure. But if you have a mapping from the data structures that microservices use and the ontology, you might try to denote or derive the semantics of microservices in terms of the ontology. And this, from a practical point of view, could be a very, very interesting task to, for the software engineer that has the control over the system. Another way to use query abstraction is to try to automatically associate semantics to open data sets. You might agree with me that many open data that you find on the web are not really well documented, right? Well, query abstraction could be one way to go to try to associate semantics to open data automatically, where semantics being annotating the open data with the concept of the ontology. Okay, let's say that now I want to give you a very brief idea of the notion of query answering and on the problem of query answering. Right. So remember what query answering means in the concept of ontology-based data management. It means to try to get to characterize the certain answers to the query, right? Now, the formal definition that has been used in order to technically solve the problem or try to solve the problem of query answering is the notion of perfect rewriting. Let's look at this definition. Let's say that you have a query QO over the ontology, right? You want to compute a certain answer. Well, a query QS over the schema of the sources is called a perfect ontology to source J rewriting of QO if for every S database D, evaluating QS over the database D coincide with the certain answer, cert QO JD. So the perfect rewriting is the query that you are looking for when you want to really compute all certain answers. Obviously, when you have defined the notion of perfect rewriting, two basic computational problems comes into mind. The first one is verification, right? I give you a QS, and you have to check whether QS is a perfect rewriting of QO. The other task is probably the most important one. I give you QO, and you have to compute the query QS over the sources, which computes a certain answer. And actually, as I told you before, computing perfect ontology to source J rewritings in several scenarios is one of the most fundamental problems in KR, in knowledge representation. And if you look at the, to the conferences on IJCAI, IIII, KR, you find, in the last, let's say, 13 years, many papers, many investigations and studies trying to solve the computation problem. Given a query over the ontology, give me the perfect rewrite. Obviously, many papers deals with this problem depending on many parameters. For example, which is the description logics used to express the ontology, right? Or which is the class of queries that I accept to express the query over the ontology, or which are the mappings that I accept. So depending on the kind of system that we have, it might be that I can really compute the rewriting, the perfect rewriting, or it might be that I cannot do it, or I can do it with a certain complexity, and so on. Okay, so I would like to, to convince you that deriving the perfect rewriting in an ontology-based data management system is not an easy task. So let me spend 2 minutes about this example. Suppose you have an ontology where you have persons, you have computer professors that are subset of persons, you have the relation heights over person, right? X hates Y if the person X hates the person Y. And then you have a supervised by relation connecting person to computer professors. And now you have in the ontology the knowledge that computer professors are partitioned into 2 subsets, computer scientists and computer engineers. Notice that this is a complete generalization, which means the following, that every computer scientist is not a computer engineer, right? But both of them are computer professors, and every computer professor is either a computer scientist or a computer engineer. Okay, now suppose that the data that you have at the sources would correspond at the ontology level, so the patterns that you realize in the ontology, looking at the data at the sources, suppose that that corresponds to such knowledge graph. Okay, so from the data at the sources and the mapping, that John is supervised by Andrea, who is a computer professor. John is supervised by Mary, who is a computer scientist. And then that Mary hates Andrea, and Andrea hates Paul, who is a computer engineer. So the graph that you see on the slide is the only knowledge that you have by applying the mapping over the data sources, right? And notice that this kind of knowledge graph is expressed in terms of the ontology. Now, please consider the query over the ontology asking for all X such that there exists a Y, Z, such that X is supervised by Y. Y is a computer scientist. Y hates Z, and Z is a computer engineer. So in some sense, I'm asking whether there is a guy supervised by someone, and this someone is a computer scientist hating a computer engineer. So I would like to give you 30 seconds. Unfortunately, I cannot interact with you, but I would like to give you 30 seconds and try and ask you to spend these 30 seconds to come up with the answer to the query. So, is someone satisfying the query? There is some X or not. The hint is that X, it might be only John, right? Because John is the only one who supervised someone. Someone. So the question could be also rephrased that, does John satisfy the query, yes or no? Okay, unfortunately, I don't know anything about your answers, but let me, in my experience, since I use this example often, my experience is that there might be many people saying that John does not satisfy the query. Why? Because probably the most natural thing to do is to try to check whether this pattern is satisfied in the graph. So where is Y? Y could be only Andrea or Mary, right? If I just reason in terms of patterns in the graph. Y could be only Andrea or Mary. If Y is Andrea, and this is not satisfied because Andrea is not a computer scientist, or at least the graph doesn't tell this. So it cannot be Andrea. On the other hand, if I try with Mary, Mary is indeed a computer scientist, but Mary doesn't hate a computer engineer because Andrea is not a computer engineer in this graph. So I think I would be tempted to say no one satisfies the pattern. Unfortunately, this is the wrong answer. Why is that? Because actually the ontology, who is very, very important in the ontology-based data management system, I cannot just ignore the ontology. The ontology tells me that every computer professor is either a computer scientist or a computer engineer. Now, the data from the sources doesn't tell me anything about Andrea. It just tells me that it is a computer professor. So the data, the sources do not know that Andrea is either a computer scientist or a computer engineer. They just know that there is a computer professor. But I know that in the world, Andrea is either a computer scientist or a computer engineer. Now, if in the models where Andrea is a computer scientist, this query is satisfied because Andrea, why is Andrea, right? Because he is a computer scientist hating Paul, who is a computer engineer. In the models where Andrea is a computer engineer, now Mary satisfies why, because she is a computer scientist who hates Andrea, who in these models is a computer engineer. So in other words, John is a certain answer. But in order to understand and to derive the fact that John is a certain answer, I had to reason by cases in the models of the ontology. And this means I can prove that this allows me to show that there is no first order query which is a perfect ontology source rewriting of Q. So if I take this kind of ontology, it might be that I cannot rewrite the query that I have into a query over the sources, which is a first order query over the sources. Okay, so it might be that I cannot do that. So so this, by the way, this implies also that computing certain answers in an ontology with an ontology of that kind is co-NP hard with respect to the size of the data. Okay, and to make the story short, what we did in our group is to design a language of the ontology in such a way that you are guaranteed that every query over the ontology can be rewritten into a first order query over the data sources, which can be written into SQL, so that you can do the following. If the ontology is expressed in this kind of language, you can do the following. You can simply do the following. You have the ontology-based data management specification. You have your database at the sources. You have a query queue, which is a union of conjunctive query. What you can do in order to answer, to compute a certain answer of Q is to, first of all, to rewrite the query into another query over the ontology, right? You rewrite the query in terms of another union of conjunctive queries, taking into account all the axioms in the ontology. You then consider this query and you rewrite it into a map, into another query over the data sources by using the mapping. And finally, you get a union of conjunctive query over the data source. Remember, the union of conjunctive query means essentially a select project join in union, and then you evaluate the query over data source and you get a certain answer. Okay, let me now go to the abstraction. So let me recap. We have techniques to do query answering over ontology-based data management systems at the price of choosing, the appropriate languages for the ontology and for the mapping. So if you choose these kind of languages, you know that pathological cases like Andreas' example do not occur, and therefore you know that you can always rewrite a query over the ontology into a query over the data sources expressed in SQL that computes a certain answer. Okay, but now let's consider the other task, abstraction. Abstraction is a completely different problem. You do not start with the query over the ontology, you start with the query over the data sources. Now you ask yourself, how can I compute the query over the data source, over the ontology that captures my query at the data sources? So you see, it's a completely different and reversed problem. But again, I have to tell you the definition, the formal definition of abstraction, right? So here, this is the most important definition to understand the notion of abstraction like we defined it. So we say that the query over the ontology, let's say QO, is a perfect J abstraction of a query over the sources. If for every S database D consistent with J, we have that the certain answer of the query over the ontology coincide exactly with the answers of QS to the database D. So in other words, QS is somehow equivalent to QO in the sense that when you compute the certain answer to the query QO, you get exactly the answer to QS. So you see, it's the opposite of query answering. But again, you can consider two basic computational problems for abstraction. For example, you might consider the notion of verification problem. I give you QO, and then you check whether QO is a perfect J abstraction of QS. More importantly, you have the computation problem. I give you QS and J, and your task is to compute the perfect J abstraction of QS. It's going to be much more difficult. Okay, so let's see an example, okay? From now on, in the last 10 minutes, I will go essentially through examples. So here the example is the following. First of all, you see the blue concepts. The blue concept constitute the ontology that we are going to consider. Very simple one. We have employees are person, students are person, persons are animal, and animal are not universities, right? So there is a disjointness assertion saying that no instance of animal is an instance of a university. In some sense, these two concepts represent the natural types in our ontology. So everything is either an animal or a university. Now, I have two tables in my database. in my data sources. I have treg and tstudent. T-registry, the table registry, essentially tells me who are the person. So there is a mapping saying that every tuple in treg is a, it corresponds to a person. By the way, the table treg has an attribute job, and when this attribute job is equal to E, then the tuples of treg would correspond to employees. So it's a very simple situation, two tables, right? One table, which is tstudent, just give me the student. Okay, it's a table containing all the students, the tuples of students. And treg, the table treg gives me all the persons, and some of the tuples of treg would correspond to employee, those that have job equal E. Now, let's consider source query QS. Select ID as X from tstudent. So essentially, I want to the query QS denotes all the table tstudent. Question for you. Is there any perfect J abstraction of QS? Which is the query at the level of the ontology that captures the table student? Well, I think you agree with me that in this case, everything is very, very simple. You have the predicate student. Predicate student is mapped exactly to the table student, so it's not it's not a surprise that the student, the query student X is the perfect J abstraction of QS. Okay. However, let's now consider the query QS prime. I want all, the query that captures at best the table treg. So which is the query at the level of the ontology that captures treg? Well, one might, might think that it's obvious that person might be a good candidate because I have a mapping, right, with person. However, if you compute a certain answer of person, intuitively, you also get student in the certain answers, and therefore you also get tstudent. So you don't get exactly treg, you also get some tuples in the other table. So person will not be a perfect abstraction. Actually, if you think about it, there is no perfect abstraction in this particular case. You cannot precisely characterize the table treg by means of a query over the ontology. So in some sense, this is a bad news, right? Because if you would like to know, if you are in an application, your information system is very complex, and say, come on, let's give me what is in the table treg. Please tell me what is it. You would like to give the answer in terms of the ontology, and you say, well, I cannot tell you, I don't know. So why? Because there is no perfect abstraction. However, what you can do in this particular case where you don't have a perfect abstraction, you might ask, okay, it is true that you don't have a perfect abstraction, but give me an approximation. Give me a query that is a sound approximation or a query that is a complete approximation. What do I mean? Well, give me a query, for example, sound approximation would mean give me a query QO such that the certain answers is a subset of the query QS. I know that it's not perfect, but at least all the answers that I get from QO are also answered to QS. Or I could ask myself, is there any query QO whose set of answers, certain answer, is a superset of QS? Well, if I go with this kind of approximation and go back to the example, I think that, although obviously the perfect J abstraction of QS is student, and although the perfect J abstraction of QS prime does not exist, I have many complete J abstractions of QS prime. For example, person is a complete J abstraction. Why? Because I'm sure that the certain answer of person include, you know, the tuples of T-reg somehow, cover the tuple of T-reg. Obviously, also animal, right, is a complete J abstraction. Although probably person is a better abstraction because it's a subset of animal. And what about a sound abstraction of T-reg, of QS prime? Well, if you think about it, person and university is a sound abstraction. Why? Because it's the empty query. If it is the empty query, empty because person intersection university is always empty, obviously it's sound. It is sound, right? But probably a more interesting sound abstraction of QS prime is employee. Employee is a query over the ontology such that its certain answers cover part of T-reg. So that, I think that's a good candidate for an appropriate sound, a satisfactory sound abstraction of QS prime. So in order to get to you know, in order to capture the idea of sound abstraction that are, you know, satisfactory, or complete abstraction that are satisfactory, we introduced the notion of maximally sound and minimally complete J abstraction, right? Obviously, minimally and maximal with respect to a class of queries. Okay, so I think that it's obvious. The definition is obvious. An L maximally sound J abstraction is a sound abstraction such that no other query is a better abstraction. It's a better sound abstraction, and correspondingly, an L minimally complete J abstraction is a complete J abstraction of QS, such that no other query exists, which is a better complete abstraction. So if you apply these new notions, then you probably come up with the idea that with you know, the observation that person is the minimally complete J abstraction of QS prime in our example, whereas employee is the UCQ minimally sound J abstraction of QS prime. Notice that I'm going to that I use UCQ minimally complete or UCQ maximally sound, and by that I mean that this is the best query in the class of union of conjunctive queries. Why? Because if I change class of queries, I might have better abstractions. So the notion of minimally complete and maximally sound is always with respect to a class of queries, right? Okay, I think I am running out of time, so I'm going to skip the some of the slides, and I would like to give you some hints about what we have done, which are the results that we have derived by studying the notion of UCQ minimally complete and UCQ maximally sound abstractions. The first idea, I'm going to go back, is that we have an algorithm for computing the UCQ minimally complete abstraction in a particular setting, where DLite is the ontology language, Gov is the mapping language, and union of conjunctive queries are, you know, the class of queries that are used to denote the query QS. In synthesis, okay, we have, you know, a good and reasonable algorithm to compute UCQ minimally complete abstractions in a reasonable kind of an ontology-based data management setting. This is interesting because if a perfect abstraction in this class exists, then it is also a UCQ minimally complete. So in some sense, if the perfect abstraction exists, our algorithm capture the perfect abstraction. Unfortunately, UCQ maximally sound abstractions are much more involved. First of all, just the verification problem for sound abstractions in the class of UCQ is pi-p2 complete, which means that it's a very hard problem. Even only verifying whether a query is a maximally sound abstraction. Also, we have figured out an algorithm for computing UCQ maximally sound J abstraction only in particular situations. And we have proved, unfortunately, that in many situations, UCQ maximally sound J abstractions of a query QS may not exist. Okay. So let me conclude because I think I'm running out of time. So what we have done on abstraction, I think abstraction is it's a nice notion. It allows you to find a query over the ontology that captures some query, some computation at the level of the data sources. Until now, we have restricted ourselves to UCQ, Union of Conjunctive Query, as query language expressing abstractions. In a recent work, however, we have started investigating more general kind of query languages that you might use to express better abstractions. Let me reconsider the query here. The query QS prime and the ontology that we have we just discussed. I think it's intuitively you might understand that if I can use negation somehow or negation with an epistemic operator, I may come up with a query that is a better sound abstraction of QS prime. Because remember, the UCQ maximally sound abstraction was employee. But if you think about it, if you take all the persons and you remove all the guys that are known to be student, then you get a query at the level of the ontology, which captures better the table T-reg. Because in some sense, you are kind of expressing at the ontology level T-reg minus T-student. Okay? So this very simple example tells you that if we go beyond union of conjunctive queries, then we might compute better sound approximation of abstractions in the cases where perfect abstractions do not exist. So indeed, we are studying many different aspects of this new idea, new notion of abstraction. I don't have the time to list all of them, but it's a plenty of open problems, nice open problems to study in this topic, in this realm. Now, let me finish by thanking many people that have worked with me in the last years, both on query answering in ontology-based data management systems and in query abstraction. And I would like to mention the fact that query abstraction is actually the topic of a PhD thesis of Gianluca Cima, who will defend his thesis very soon. So thank you for your attention.